Hey Team Bio, today's screencast is going to be about the greenhouse effect, how it relates to climate change, and we're going to talk about a little bit of physics in order to understand what is happening with greenhouse gases and the Earth's temperature. Okay, so let's talk about the electromagnetic spectrum. You've seen this image already. You know that we have high frequency, small wavelength, high energy waves, electromagnetic waves called gamma rays, and then low frequency, long wavelength, low energy waves, radio waves, and then everything in between. This is the entire electromagnetic spectrum. Visible light makes up a very small fraction of the spectrum. Okay, where is the electromagnetic energy coming from? Well, every object emits radiation at all times and at all wavelengths. Right now, you are emitting X-rays. This is actually true. However, the wavelength of peak emissions is inversely proportional to the temperature of the emitting object. That's kind of complicated. What does that mean? It means that while all things are emitting all types of radiation, the most radiation that they emit is going to be proportional to their temperature, or I guess their wavelength is going to be their frequency is going to be directly proportional to their temperature, and their wavelength is inversely proportional. What does this mean? Hot things. On this side, cold things. On this side. Anyone who has ever built a fire knows that a fire is emitting visible light. It's quite hot. As a pan heats up, it might turn red. It's going from emitting infrared light into visible light. You know, the hottest part of the fire is the blue part. Yes, so what am I trying to say here? Hot things emit light in this side, cooler things emit light in this side. If we were to look at the emission spectrum of the sun, we would see that most of the light that it's emitting is visible light, but it's also emitting light in the ultraviolet spectrum and the infrared spectrum. It is pretty hot. The Earth is also emitting light, but it's colder than the sun. It's emitting in the infrared spectrum. So that's an important idea. Every object emits radiation at all times and at all wavelengths, but the most radiation that objects emit is going to be proportional to the temperature of the emitting object. The wavelength of peak emissions is inversely proportional to the temperature. So that means small wavelength things are going to be very hot, and big wavelength things are going to be emitting mostly cold. No, cold things are emitting mostly big wavelength things. That's the way I want to say it. Okay, so that's our first idea. Our second big idea is that different materials have different transparencies to different wavelengths of light. Well, what do I mean by that? Okay, glass. Glass is transparent to visible light. It allows visible light to pass through, but it is opaque to infrared light and to ultraviolet light. You can't sit behind glass and get a sunburn because ultraviolet light is absorbed by the glass. X-rays. X-rays, relatively high energy type of wave, is transparent to most soft tissue. But it's absorbed by the calcium that's in your bones. This is why we use it for taking images of bones. It passes through, it's transparent to most soft tissue, but it's absorbed by bones. So replace this glass with bone and this with a picture of you. Okay, what else? Wi-Fi signal. You might not be in the same room as your router. Wi-Fi is transparent to your walls, but it is absorbed by other things. I don't actually know what absorbs Wi-Fi. Okay, radio waves. Radio waves can pass right through the walls of your house. And again, I'm not quite sure what radio waves are opaque to. Okay, so those are our two big ideas. Things are emitting all frequencies of light, but mostly they're emitting the light that's proportional to their temperature, and that all materials have some types of light that they're transparent to and some types of light that they absorb. Okay, so when we look at the Earth's atmosphere, we see a situation like, no, that's not the way I was saying. Okay. Okay, here is an excellent photo. It is showing you the greenhouse effect, which is a combination of the two things we just talked about. The sun is mostly emitting visible light. Some of that light is coming down and is bouncing off the atmosphere and going back out into space. Actually, about 30% of the light that the sun emits that hits the Earth just bounces right off. 20%, I want to do this in black. 20% is absorbed by the atmosphere itself, and 50% of the light that hits the atmosphere passes through the atmosphere, and hits the Earth itself. It comes out to about 340 watts per meter squared of energy. Light energy is striking the Earth all the time. So if we take the total Earth, so some parts of the Earth are getting more sunlight than other parts. You know that from earlier screencast. And obviously the day, you're getting more light than the night when you're not getting any light. But if we take all of that total sunlight over the entire Earth and we averages out over a year, we find that every meter squared gets about 340 watts of sunlight all the time. Okay, the Earth absorbs that energy, but the Earth is not as hot as the sun. So while visible light comes in, IR, infrared, is emitted. Okay, so the Earth is absorbing visible light, but it's re-emitting that light as infrared. Okay, so let's talk about a greenhouse. A greenhouse works because it is transparent to visible light. Visible light can come through the walls of the glass, and that visible light is absorbed by the plants in the greenhouse, and that energy is going to be because plants are not very, very hot, or the greenhouse itself, the Earth in the greenhouse is going to re-emit that energy as heat energy. However, the glass is not transparent to the heat, and so the heat is trapped in the greenhouse. It cannot get back out. So sunlight can come in, heat light can't get back out. That is the greenhouse effect in a greenhouse. The same is true of light in the atmosphere. Sunlight is transparent to the atmosphere, but there are all these tiny little particles in the atmosphere. So the atmosphere, remember, is made up of a bunch of different things. We got a bunch of N2, we got a bunch of O2, we got a bunch of CO2. And CO2 is really good at letting sunlight pass through, but then absorbing IR light. So CO2 will trap this infrared light, just like the greenhouse glass panels are not allowing this IR infrared light to pass back through. CO2 is not allowing this infrared light to pass back through the atmosphere. So it's trapping it. This is a good thing. Without trapping heat energy at all, the Earth would be super, super, super cool. Super cold. It would be freezing. It would be like a giant ice ball. So we need greenhouse gases. However, the Earth's energy balance is changing as we increase the amount of CO2 in the atmosphere. And let me tell you what the energy balance is. Okay, energy balance. I guess I should say Earth's energy balance. Okay, Earth's energy balance. If the temperature of the Earth is constant, this means energy in has to equal energy out. So we know that we have 340 watts per meter squared coming in, being absorbed by the Earth. And in order for the Earth to stay at a constant temperature, 340 watts per meter squared has to be re-emitted. Now, let's talk for a second about a concept called radiative forcing. Okay, radiative forcing is when the energy in is not equal to the energy out. If we have a positive forcing, this means the energy in is greater than the energy out. And the result of this is an increase in the temperature. If we have a negative forcing, this means the energy in is less than the energy out. And this will result in a decrease in temperature. Okay, so this is a little easier to understand maybe when you talk about it with a pan on the stove. Okay, before the stove is turned on, we have a pan. It is at room temperature. It is emitting mostly energy in the form of heat, but as you know, this pan is at room temperature. It's not emitting a bunch of energy. It's actually at a constant. The energy in is equal to the energy out when it's at room temperature. It's not changing its temperature. But what happens when we turn on the stove? Okay, so now we've increased the energy in. The stove is lit, and the energy that's being absorbed by the pan is more than the pan is emitting. So because the energy in is greater than the energy out, and we have a positive forcing, the temperature of the pan is going to heat up. But the pan is not going to heat up indefinitely, or it's not going to heat up to, what do I want to say? Infinity. It's going to stop heating up when the energy that the pan is emitting is equal to the energy put in by the stove. So the pan is going to reach a steady state in which the energy supplied in by the stove is equal to the energy that is shed off by the pan. If you've ever left a pan on the stove for a period of time, maybe a longer period of time than you intended to, you might notice that the pan didn't melt. It actually reached a steady state where the energy that the pan is getting from the stove is equal to the heat that the pan is releasing. So, no, we no longer have a radiative forcing. Our energy in is equal to our energy out, and the pan's temperature doesn't change. It's at a constant high temperature of hot. Don't touch it. Okay, we turn the stove off. Now, the energy out is greater than the energy. And what's happened? The temperature is increasing. The pan is emitting more heat than it's receiving from the stove. And we have a negative forcing. Okay, how does that relate to the Earth? Well, we know that we have 340 watts per square meter coming in of energy from the sun. And in order for the Earth's energy balance to stay constant, it has to re-emit 340 watts per square meter. However, as we increase the amount of greenhouse gases in the atmosphere, CO2 and CH4 and N2O, what is happening is that these greenhouse gases are absorbing this infrared energy, and they're trapping it in the Earth's atmosphere. So now we are receiving 340 watts per square meter of energy from the sun, but we are not emitting 340 watts per square meter because we're trapping it in the atmosphere. And that is the greenhouse effect. And that is why the Earth is heating up. Okay, that is all. See you in class.